I now want to resolve the problem using conservation of energy. So the big difference here is how we choose the system. So if we choose our system to be the car and Earth, then gravity will not change the total mechanical energy. So if we rethink our system, and we draw, let's say that this is part of the roller coaster. So what we want to pay attention to is that we have Earth here. So if we have our cart in this position here, then our system not only includes the cart, but it also includes the Earth. So what I'm seeing here is that there is the force of gravity within the system here. Now note, I'm going to ignore the normal force because in the previous example, when we used the work energy theorem, we saw that the work by the normal force was 0. So now, if I now apply the work energy theorem, we then say that the network is going to be any external work plus the work of gravity, and this is going to change the kinetic energy. However, we have already shown that the negative of gravity is the change in potential. So if I rewrite this thing, okay, so now if I rewrite this expression, I then see that I'm going to get that the external work is then going to be the change in kinetic energy plus the change in gravitational potential. So then we ask the question, are there any other forces besides the force of gravity and the normal? Now remember, we already said that the normal, the work of the normal is 0, so that one doesn't count. And the answer is no. No external workings, which then implies that the external work is 0. Because of this, we further rewrite this as, we then say that 0 equal to the change in kinetic energy plus the change in gravitational potential then leads to K1 plus UG1 equals K2 plus UG2. And this is conservation of mechanical energy. And even though I did not write this, this has to remain a constant. So now if we use our picture from last time, so now to draw a bar diagram, I could then come in and put this in. So this is what we had last time. We had this system. And now what we're doing here is that we're going from A to B. So if I look at this thing, here's what I'm going to see here. If I look at my point 0, I can see that this is the height the gravitational height at this thing, and then this cart is actually moving at this point. And it's going to be moving with kinetic energy like this. And what this tells me is that because there are no external works, every point along this path, this is a constant. And this is what we mean by the total mechanical energy being the same. So when I get to point A, we can see here that I still have the same height. So my gravitational potential at A is this, and my kinetic energy at A must be exactly at point 0. So when I get to C here, or B, excuse me, you could see that I have to have a lower height, and we are automatically forced to say then that the rest of this must be kinetic energy at B. So as expected, if you're going to go downhill, you would expect to be moving faster. And that's what that higher kinetic energy. If I'm higher, if I start to go uphill, we would expect that you would be going slower. So now I could then say, from conservation of mechanical energy, I could then say that the energy at A has to equal the energy at B, and this has to be a constant. So then it says that the kinetic energy at A plus the gravitational potential at A has to equal the kinetic energy at B plus the gravitational potential at B. And so then I continue to rewrite my expression. So then I'm going to go 1/2 mVA squared plus mg, and this will be YA. Then I'm going to have 1/2 mVB squared plus mgyb. Again, as we showed before, this is a mass-independent result, which implies all masses cancel. So now I can isolate VB. So if I isolate VB here, it then tells me that then VB is then going to equal to VA squared plus 2G YA minus YB with the square root. And again, if we look at this thing here, we saw here that YA minus YB, note that there's no minus sign here. This is going to be H minus 1/2 H, which is then equal to 1/2 H. So if we plug in all the numbers like we did before, this is now 26.5 meters per second, and that is what VB is, which is exactly the same answer that we got beforehand. So now we could come in and we could repeat this process again for part B. So in part B, what we want to do here is that we want to determine how high the car goes up the last hill. So again, if we use our picture and modify it, so this is what we initially had. So then I'm going to modify what we have here. I'm going to only focus on B here and C. So I imagine that I have my cart and some point up here, the cart gets to right here. And we know that at this point, this cart here reaches max height, which implies then that the speed at VC is equal to 0. So that means that its maximum height will be this YC relative to the ground. So now what we will do here is that we want to focus. So our focus is on the path B to C. So our bar diagram reads something like this. So I see that the cart initially starts with a certain amount of potential energy right here. And this is going to be the gravitational potential energy at B. But it has potential energy. So when I look at the, kinetic energy, so now I know that it has this amount of kinetic energy at B, because from our previous example, we saw that it was moving faster at point B. So when it gets all the way up to the point here, we know that the car at C has stopped moving, and as a consequence, all of this energy now is in the form of potential energy, and therefore we have this. So our bar diagram then shows that according to conservation of mechanical energy, we see here that this is KB plus UGB has to equal UGC. So now what we want to focus on is that we now want to calculate the height YC using conservation of mechanical energy. So then I just start to write it down. And here we go. We then say that we have KB, or maybe we should start a little bit more cleaner and say, this is the energy at B, and this is the energy at C. So this has to be KB plus UGB equals UGC, which then means that I have 1/2 MVB squared plus MG YB equals MGYC. Again, because gravity is the only force, it's always going to be mass independent. So now I'm going to isolate YC. So if I isolate this, doing a little bit of algebra, then this is then going to be VB squared times 2G. And then here's what we know. We know a couple of numbers already. The one that we want to think about is that we saw that this was 1/2 h, so this turns out to be 21 meters, and we already computed VB as 26.5 meters, so if I plug everything into here, I get the value of 56.8 meters, which is exactly the same answer that we got beforehand.